In the previous class, we studied about electric field and its properties. Before we move on to the content for this class, we are going to revise a few important concepts from this chapter that we have studied so far. So, I'm going to write these things on the board. You try to answer these questions on your own. Okay, let's start. So, first of all, charge is a scalar or a vector? Come on, answer it quickly. The next question is, what is quantization of charge? Answer: it is the idea that charge of any object is in steps of some fundamental charge or integral multiple of the fundamental charge E, which is nothing but the charge of the electron. Third, the Coulomb's law. I hope you remember the Coulomb's law. Try to say the formula or the sentence for the Coulomb's law. The formula is that Coulomb's law in vector form is force applied on charge 1 by the charge 2 is equal to K Q1 Q2 by R12 squared R12 hat. Obviously, the unit vector indicates the direction from vector 2 to vector 1. Next is, what is the value of K in SI units? Then, what's the relation of K with epsilon 0? Hopefully you remember the name of this quantity. Epsilon 0 is called the electrical permittivity of free space. Right? So hopefully you can write down a relation between K and epsilon 0. Right? The next thing is electric field produced by a point charge. Its expression is given by E vector is equal to it is KQ by R square R hat. Obviously, you should have answered this one very well. The relation between K and 1 and epsilon 0 is K is equal to 1 by 4 pi epsilon 0. So if I use that here, I can always write this down in this manner. Right? So that's what we have studied so far. Okay. Now we're going over to the content for this class. We are going to study two important things, two important concepts in this lecture. The first one is electric field due to multiple charges. If you remember, when we studied about the electric field produced by a point charge, again, a point charge, just a single point charge, capital Q, right? Now here we are going to think about what would happen if there are multiple point charges instead of just one, right? So what we have is there are many or multiple source charges, and each of the source charge creates its own electric field, and then finally the net result or the end result is that the electric field of all these source charges combines with each other, adds up to each other, and produces a net electric field. So that's what we are going to talk about. It's very, very close to the superposition principle of forces, right? Okay. So let's say that in a typical situation, we have got 3 point charges Q1, Q2 and Q3, and let's assume for simplicity again that all of them are positive. So we have got 3 point charges Q1, Q2 and Q3 placed at these 3 points in the space. And now I want to find out what is the electric field at this point P due to the combined effect, or what's the net electric field at the point P due to all the 3. Okay. So let's get started. Again, if you remember, what's the method to find out or to measure the electric field due to a charge? And the method is you put a test charge. I hope you remember. You put a test charge, and then you find out the force acting on that test charge, and then you divide that force by the magnitude of that test charge. So basically, what I'm saying is, we can say that the electric field at this point will be the force acting on the test charge divided by the magnitude of the test charge, right? So that's the procedure. So we are going to repeat that procedure over here. The only difference between what we discussed in the previous lecture and this lecture is that here you have multiple charges, so it's not going to take a lot of time. It's fairly simple. Let's start. So I'm going to put a Q charge over there, which is obviously the test charge. Okay, it's a positive test charge, like I mentioned it earlier, we put it to be positive. I'm going to define 3 vectors. This vector, I'm going to say this is position of P with respect to charge 1. Okay, this is position vector of P with respect to charge 2, and similarly this is position vector of P with respect to charge 3, Q3. Okay, so what we have now is we've got 3 vectors which are indicating position of the point P with respect to these charges. So first of all, we think of the force acting on test charge due to Q1. Okay, so let's talk about the force that is acting on the test charge Q due to Q1. So that is going to be F on Q due to 1. Okay, I hope the symbol is right here. And in vector form, it's going to be K, capital Q, small q, Q1, that is capital Q1, Q divided by, what's the distance between Q1 and P? Well, that is RT1 and it's squared, so that's the magnitude. And now, the direction, so that is going to be RT1. Now, just like that, similarly, again very quickly, write that FQ2 and FQ3. Okay, so FQ2 is going to be K Q2 Q by RT2 square RT2 half. Right? I don't think you have any problems whatsoever understanding that. And this one I'm leaving it for you to figure out yourselves. Okay, so what we have got now is we have got the forces acting on this one due to all the 3. So let's see the directions again. So if everything is positive here, you have FQ1 in this direction, force on Q due to the first charge, force on Q due to the second charge will be in this direction, and the force on Q due to the third charge is in this direction. So the net result, net force will be the addition or the superposition of all the 3, right? So if I want to write down the expression of the net force, if I want to write down the expression of net force on the charge, on the test charge, net force on test, excuse me, I'll just write that again, just to make sure that you can read it. Net force on test charge Q is FQ vector, which is going to be equal to FQ1 vector. See, there are 3 forces acting on the charge Q, and FQ3 vector, all the 3 add, correct? And now I'm going to just put in these expressions, okay, that we have figured out already, and I'm sure you realize what we have is I can take Q common out of the whole expression, right? For the whole bracket over here, Q is common. So what we get is K Q1 by RP1 square RP1 hat plus K Q2 by RP2 square RP2 hat and plus K Q3 by RP3 square RP3 hat. Okay, so that is what we have, right? Now, as you would have noticed already, that if we want to find out the electric field at point P, due to what? Due to net effect. Let me just write net over here. So net electric field at the point P due to which charges Q1, Q2 and Q3 all the same together. Okay, so net electric field at the point P due to Q1, Q2 and Q3 is E vector, which is again going to be FQ vector divided by Q. This is the basic definition of electric field. The force acting on a unit positive test charge at a point, right? So this is the force acting per a unit positive test charge or per the magnitude of the charge, right? So what we get is, now if I simply use this expression that I've got here, FQ vector divided by Q. Okay, so that is going to give me K Q1 by RP1 square RP1 hat plus K Q2 by RP2 square RP2 hat and just like that K Q3 by RP3 square RP3 hat. So what we are noticing over here is that just like the forces are added in the vector form, I could say that this is the contribution or this is the electric field due to the first charge Q1. Just like that, this is the electric field due to the second charge Q2 at the point P again. All these fields are at point P. So they are the contributions of the individual single charges Q1 and then you do the second one Q2 and then you do the third one. Right? So just like you will say that the net forces on Q are as follows. Okay, just like that, using this idea, you will write it as follows: that the electric field at the point P, remember, electric field is the property of point in space, it's not the property of test charge. Okay, I hope you remember those important points that we talked about yesterday. So, electric field at P, it's a vector, is equal to EP1 vector. That's this. This is EP1 vector because this is the contribution of the first charge for the electric field at P. Right? See, if you simply ignore these terms, right? This is what you get as the electric field at P. Then similarly, the second term over here, that's the contribution of the electric field at P that's coming from the second charge, Q2. And finally, the third charge. So what we can see over here is actually the superposition principle. What I mean to say is, suppose there was only one charge, Q1, then the electric field would only have this term in its expression. But because there's a second charge, what we are having is that the first charge doesn't bother whether there is a second or not. The electric field created by the first charge still remains the same. And similarly, the second charge doesn't bother whether there is charge 1 or charge 3. The electric field created by the second charge does not depend on anything else, right? So, what we are having is presence of other charges does not change the effect of a charge, correct? So just because Q2 and Q3 are there, electric field due to Q1 is not going to change, right? But remember that this net electric field at P, the net electric field at P is due to all the three charges, right? So what this means is that when there are multiple charges, again, that's the topic we are having up here, electric field due to multiple charges, right? So when there are multiple charges, each charge just does its own job. It doesn't bother, there's really no interference. Basically, presence of other charge doesn't affect this charge, right? So that's what we have here. So this is actually the superposition principle for the electric field, right? So just like in Coulomb's law or Coulombian forces, presence of a third charge does not affect the forces between charges Q1 and Q2. Just like that, presence of other charges does not affect the electric field created by the first charge, or presence of 1 and 3 doesn't affect the electric field created by the second charge. It still remains kq2 by rp2 square rp2 hat. Okay, so now keep this important lesson in mind. Along with it, I'd like to draw your attention. Look at this carefully. It's all vectors. That means you cannot add magnitudes of electric field. I hope you remember that common mistake about students adding forces magnitudes. Okay, so remember, do not add magnitudes of electric fields because they are vectors, just like forces are vectors. Okay, so that's what we have for this topic. We're going to practice questions about this, this concept, but there is a related concept that I want to cover first, and then we'll solve questions regarding both of those. Okay, so let's start with that. So now we are going to talk about force on a charge in presence or inside of an electric field. Okay, so read the diagram carefully. I'm going to very quickly draw a diagram that will indicate what we are talking about here. We're saying that this charge which is present or which is inside what? Inside an electric field. Okay, think about it. You take a piece of iron, okay, and let's say there's a magnet nearby. So this piece of iron would be inside the magnetic field, that's what we say. And because of that, the piece of iron experiences a force. Correct? Okay, so just like that, suppose in this region, let's say that in this region, somehow some electric field is present everywhere. I'm just indicating by the E vector. Okay, so let's say somehow over here, in this space, electric field is present. Okay, now it's quite possible that the electric field is varying or it's not same everywhere. I hope you remember what I told you about wind and what I told you about fields. Okay, wind velocity, that is wind speed, and wind direction may be different at different places on the earth at the same time. So just like that, varying field, varying electric field, that is at different points electric field could be different. Okay, so let's say that at this point over here, which we are going to call P, point P, at the point P, we are putting some charge. Okay, we are putting some charge. Now that may be a test charge or maybe any other charge, no problem. That's it, a charge. Okay, so let's say there is some charge Q over here. Okay, there is some charge Q placed over here. Now, it's important to distinguish the charges that create electric field and this charge which is placed in the electric field. I want all of you to go back to this case again. Okay. If needed, move the videos a few seconds, maybe a minute or two backwards, and see the diagram again. It's that we put the test charge Q. Obviously, the test charge Q does not apply force on itself. Okay. But the other charges, the three charges, capital Q1, capital Q2 and capital Q3, they apply force on that test charge. Right? Okay. So what we were saying is that the charges Q1, Q2 and Q3 together have created something called the net electric field E vector. Okay. And they are together, all the three charges, they are creating the electric field E vector. And together, all the three charges are applying a net force on the charge Q. Then the same idea here. So let's say that there are maybe hundreds or millions of any number of charges that have created this electric field. Okay. So what I'm saying is there may be many charges which have created this electric field. Right? We don't know how many there are and we don't know where those charges are. Doesn't matter. But let's say if due to all those charges, the net force on Q is Fq, isn't it? The net force acting on Q is Fq vector, right? Okay, and we can say that at point P, all the source. Okay, sorry. Yeah, I'll just repeat what I've said. I don't think you could read it over there. So what we have is that we've got an electric field in this space. This point P is where we have put a charge Q, right? So I'm saying that net force acting on P, on the charge small q, right, due to all source charges is Fq vector. Correct? Okay. All the source charges. I don't know how many there are. I don't know where they are, but they are somewhere in the space, right? So all those charges together, they are applying a net force on this charge q, and that is Fq vector. And now, if I think of electric field at point P due to all these source charges. Again, the source charges are those charges that have created this electric field. Okay. So, electric field at point P due to all these source charges is, let's say, EP vector. Right? Or you can just write, fine, EP vector. P indicates the point, so that's going to help you more. So I can relate this net force acting on the charge and the electric field at that point by a very simple relation, and that relation is Fq is going to be equal to Q multiplied by the electric field vector at the point P. This is an extremely important relation, which obviously comes from this definition of electric field at P. What's that? Electric field at P is given by the force acting on that charge Q at that point, and that divided by the charge Q itself. So obviously these two relations are equivalent of each other, but yet I'd say that this is what we tend to use so much more, right? So what does this relation tell you? It tells you that if you've got some electric field in some space, and in that space you put a point charge Q that may be positive, may be negative, may be test charge, no problem, doesn't matter. What happens is when you put that charge Q over there will be a force acting on that charge Q, and that force will be equal to charge Q multiplied by the electric field existing at that point P. Okay, so when you put the charge at point P, there will be a force on that charge which will be Q into EP. Let's say in this same electric field at some other point, let's call this point R, and you put some charge Q dash over here. Right? If you're going to put a charge Q dash over there, then the force acting on that charge Q dash will be equal to Q E P vector. Is that correct? Is that correct? No, it is not. I hope you realize that we are not putting the charge Q dash at P, we are putting it at the point R. Okay. So that's why I cannot use the electric field that was at P point. No, because just like I said it earlier, the wind speed and direction right now in Ahmedabad is not going to be same as the wind speed and direction right now in Mumbai. So at different places, just like wind speed and direction is different, electric field may be different. So there's no guarantee that the electric field here and there is same. So we have to write ER vector, not EP vector. Because, and again Q dash over here, because the charge that we are putting is Q dash, not Q. So what we have is, if you put the charge Q dash at this point, okay, if we put the charge Q dash at this point R, then we must write ER vector first of all over here, and we should write Q dash, so that will give us the force on the charge Q dash placed at this point. Remember, who's applying this force? The answer is all the source charges together that have created this electric field. Alright, in this space, right? So again, you could think of it as electric field is created by all those source charges. Whenever charge comes inside that space where there is electric field, this charge is going to experience a force. Obviously, yes, because charges apply forces on each other, right? So, how much force does that charge experience? Well, you could say that the charge Q over there at P will experience a force Q into EP, right? So, you may start thinking, what's the need of using electric field to find the force? See, it's a very simple idea. Think about it. Let's take an example of what I'm trying to suggest. Could we not find the force directly? We have studied Coulomb's law. Why are you making us study one more thing? Couldn't you do it simply like this? Well, let's say there are two charges that are going to create the electric field. So instead of talking about electric field, why don't we simply say that the force on Q, which is at this point, is force on Q due to charge 1 and force on Q due to charge 2. That's it. Why should I use a relation like this? F vector is equal to Q E vector, and let's say this point is P. So force on Q is Q into EP vector. Why should I even bother with this? Okay, you might have a question like that. To find forces, we don't need to find P. We could use Coulomb's law. Put the expression here, and it could be done. But we don't do that. Why? The reason is sometimes the charge distribution, the way these source charges are, it makes it tough to calculate the forces individually. What do I mean? Here you have only two charges, fine, no problem. Okay, you don't have any problems whatsoever with that, right? You get what I'm saying? But assume a case where there are millions of charges. Let's say on some, something like a straight line. Okay, Q1, Q2, Q3, Q100, Q10,000, Q1 million, and so on. So what you are going to have to do is you will have to find out the forces acting on Q due to all these charges. Right? Instead of that, think about it. Instead of that, someone measured the electric field. Instead of that, if someone measured the electric field and gives you a value that is magnitude and direction both for the electric field at this point P. And now if you are supposed to find out the force acting on the charge Q, which is placed at that point, now you don't have to add up a million terms. All you have to do is, you know the effect created by all these charges at this point. At this point I said, not charge. At this point P, because electric field is property of point in space. So you know the effect created by all these million charges at this point. Understood? And now all you have to do is, we know that the force that will act on it is simply Q, that is the charge Q multiplied by the electric field at point P. And you would immediately know the force acting on that charge Q if you place it over there. Right? So, what's the advantage again? Simplicity is the advantage. When we talk about electric fields, it's very simple, very elegant to find out the forces acting on the charges. Okay, right? So again, you should realize that this FQ vector, that is the force acting on this charge Q, is not just force applied by Q1 or Q2 or Q3 or Q4 or anything. It's actually going to be the net force applied by all these charges on the charge Q. Okay, right? So all that information about where these charges are located, what's this distance, this one, they're all weighing. All that information is actually contained in this one simple electric field value. Got it? Right? That's the advantage of this expression. Okay? So, please try to remember this expression. Read it as, if we put a charge inside electric field, okay, let me just write it. Okay, let me write it here. Force acting on a charge Q placed at a point P in space or inside an electric field. You could write either, doesn't matter. Is F on Q, the vector, is equal to charge Q multiplied by the electric field at the point P. This is very important for us. Okay, right? So remember, if you want to find force on a charge, there are two ways to handle the situation. One, use Coulomb's law for all those charges that are applying force on that charge Q. That's method one. It's easy for 1, 2, 3, 4 charges, okay, but it's quite cumbersome if someone gives you 10,000 charges or 1,000,000 charges or even more. The second method is here, that instead of trying to find individual forces, somehow if you know the electric field at that point where you are putting this charge, once you know the electric field, you just multiply it by the charge Q that you have put up there, and that's it, and you get the force. Right? So that's the reason why we need this. That's the reason why I encourage you to use this formula. Right? Okay. So that's what we have about the electric field, right? And now, what we are going to do is, based on this, I have to write a few more important sentences for you that should be a part of your notes. You should remember those. It's come directly from this expression. So here is sentence number 1. Okay, it is that force on a positive charge placed inside electric field is in same direction as E vector, or in words electric field intensity, I hope you remember this, at that point. Well, what am I saying? So let's say there is a positive charge Q which is placed over here, and at this place suppose the direction of electric field is in towards the right hand. Then because of this electric field, the charge Q will experience a force. Right? Again, who has created the electric field? There are some other source charges, but we don't even bother where they are, because if you know about electric field, that's it. You know everything. Okay, you don't need to worry about where those charges are, what's their magnitude, etc., etc. So, the electric field at this point is towards the right hand side. And then because this is a positive charge, this positive charge will experience a force towards the right hand side because of this electric field. Warning, this charge Q has not created this field. One charge cannot apply force on itself. Don't forget that. Right? So, the electric field has been created by the other source charges, right? Not this one, right? So, because this charge is positive, it gets force in same direction as electric field. Now, how do we know this? Well, all answers lie in this equation. Charge is a scalar. So, if you multiply scalar with a vector, the direction will be same if the scalar is positive. Correct? I hope you remember this. We used to write it like this. It's like if you have B vector equal to K into A vector, where K is a scalar. Do you remember that? Okay, so that's what we are using over here. If K is positive, direction of B vector and A vector is same. That is just like that. If Q is positive, direction of force on Q and electric field at point P is same. And then the opposite case. So this is for a positive charge electric field. I'm not going to write the sentence. I would like you to write it on your own. Okay, write the sentence on your own. But I'm going to draw a diagram. So let's say there is a negative charge Q placed over here, and the electric field at this place is towards the right hand side. Okay. Then in which direction would this charge Q, which is negative, experience of force? Go to this equation. Put a charge Q inside an electric field. Now it's going to experience a force given by this expression, this formula. Q is negative. Come to this scalar that is multiplied with vector. Scalar is negative, so that means direction of B vector, A vector is opposite, and that's why the force acting on charge Q will be opposite. So if you have to write a sentence like this, I hope now you know what could change. It's that force on a negative charge placed inside an electric field is in opposite direction, not the same. Don't write not same, write opposite. Opposite direction of electric field at that point. Okay, so if electric field is towards the right hand side, the force on that charge is going to be towards the left hand side. Alright, so that's what we have for the force acting on the charge due to electric field. Don't forget, when I say due to electric field, it's really that it's due to the charges, okay, that have created the electric field. But like I said, once you know the field, you don't have to worry about the charges that create that field. Okay, so now let's solve problems. Okay, so first of all, we are going to solve example 1.8 from the book. Okay, so please raise the board and then I shall read the question for you. Like I have maintained earlier, please sit with your textbooks, notebooks, and everything. Okay, this is not a movie that you could watch without using any of the education tools. So please remember, you have to work on your own. Okay, so example 1.8. Yes, here it is. So the question is that there's an electron. Okay, an electron falls to a distance of 1.5 centimeter. Electron falls to a distance of 1.5 centimeter in a uniform electric field of magnitude 2 into 10 raised to 4 Newton per Coulomb. Right. So let's say in this space there is electric field. Okay. Right. The thing is that you can represent electric field by drawing arrows or lines. Like I said earlier, we're going to study about why we draw lines and all that later. I'll just draw it over here. So the electric field is given in the question, figure A, because we are talking about an electron right now. So that electric field is indicated by these upward lines. So the direction of electric field is upwards. Okay, right? I don't want you to be confused over here. This information is given in the question. Right? This figure is a part of the question. Right? You can see that there are blue lines indicated in the textbook. These lines, they indicate the electric field's direction. Okay, the arrows are upwards. Right? So the electric field is upwards. Okay. Let me just read it again. What is the magnitude of this electric field? Well, it's electric field of magnitude 2.0 into 10 raised to 4 Newton, Newton per Coulomb. Right? There's one word over here which is uniform. What is that? If you remember uniform velocity, it was something that velocity doesn't change with time. That's called uniform velocity. Right? But now, as far as electric fields are concerned, you need to understand that uniform and constant are two different terms. They mean different things. Let me show you what I mean. What uniform means over here for the electric field is that the value, the magnitude and the direction is not going to be different at any point. At all these points, the magnitude of the electric field is 2 into 10 raised to 4 Newton per Coulomb. At every point. Not only that, the direction is also the same, upwards. Right? Suppose it would be like over here, the direction is upwards, but at this point the direction is towards the left side. No, then such an electric field, that electric field at P is upward, but electric field at this point R is towards left side. Such an electric field cannot be called uniform. So uniform means, let me just write it over here, you could note it, there's no problem with it, it's an important word. Uniform means does not change with location or position or place. Does not change with position. That's called uniform field. Okay. On the other hand, the word constant means does not change with time. See the difference? Okay. There is a difference. Right? Okay, uniform means does not change with place. Same everywhere, that would be called uniform. Right? Okay, but if something does not change with time, always remains the same. I'm not saying remains the same everywhere. So uniform means remains the same everywhere. And constant means remains the same always. Right? Okay. So please remember that these two words are different. Okay. Sometimes you may have a combination of these words that it gets very complicated very soon. We're not going to do all that at the moment. So what we have is a uniform electric field here. Uniform electric field means the field is same everywhere, not just in magnitude, but also in direction. So same everywhere, not like this. Okay, so this one serve a purpose here. So what we are given is that we have a uniform electric field, its magnitude is 2 × 10⁴ Newton per coulomb, and the direction of that field is upwards. And in this field we are placing an electron, E minus. That's the symbol of electron. So here we have got an electron. Remember, electron is positively charged or negatively charged? Right, negatively charged. So electron is negatively charged, and we are going to put it over here. False. Please give it falling. Okay. In this figure A, right? So we are talking about A at the moment. Let me just clarify that. Okay. And then part B is about direction of field is reversed and keeping its magnitude unchanged, and proton falls to the same distance. That's B. We will not worry about B right now. Okay. Compute the time of fall in each case. That is for both A and B. That's A for electron, B for proton. For both of these cases, we have to find time of fall in each case. Time of fall, that is, think about this electron over here. It's a negatively charged particle. In which direction will this electron have force acting on it because of this field? Electron is a negatively charged particle placed inside this electric field. Use the concept that we have learned. And whenever you put a charge Q inside an electric field, E vector, right, the force acting on that charge Q is given by Q into E vector, where electric field is at that point. So electric field at this point is upwards, and the force acting on this charge will be downwards because the charge is negative. I hope you realize what I have written over here. Okay, right? Minus E vector, because the charge of the electron is negative E. Right? Understood? So the force on this electron is downwards because electric field is upwards. Those sentences, again, two sentences that I made you write. Okay, if you put a positive charge in the field, the force on the charge is in direction of it. But if you put a negative charge in the field, then the force on that charge is in opposite direction to the field. So this is going to be downward. So what happens is that the force on electron, Fe, okay, let's say the force on electron is going to be in downward direction. So that's why it's going to fall from this point, the highest point, to the lowest point. So how much distance is there? It's given to us in the question that this distance is 1.5 centimeter, mentioned in the first line of the question. Electron falls to a distance 1.5 centimeter. Okay, right? It falls to a distance of 1.5 centimeters, all the way from there to here. Right? Why is it coming down? Is it due to gravity? No, we are actually ignoring gravity over here. It's coming down because of the electric field. Field upwards, force downwards. Okay. So force on the electron, like I mentioned earlier, is minus E vector. And in magnitude form, only the magnitude, it's going to be 1.6 in 10 raised to minus 90. Remember, I'm not writing the minus sign because we are talking about the magnitude into electric field's magnitude is 2 into 10 raised to 4. It's same everywhere. That's why this is not going to change. That is, the force is constant. It's not going to change because as it falls down, electric field magnitude does not change. Uniform field. So finally, this is going to be 3.2 into 10 raised to minus 15 Newton. You might think that this force is very small. Yes, the force is very small. It's actually very small. But the problem is electron is a very tiny thing. It's very, very small. So we have to find out the time that it takes to go from here to here. Kinematics, isn't it? I told you it's never going to leave you. Okay, it will haunt you. It will come back again and again and again to haunt you. Well, so what we have is, we have got this force acting on the electron. We can find out the time that it takes to go from the point A to the point B if you could find out the acceleration of electron. Okay, to find time you have to find acceleration of electron, isn't it? Because here acceleration is constant. The reason is that force is constant. It's not going to change at all because that falls down, feels magnitude is uniform. This doesn't change, so this doesn't change. Right. So ultimately, to find acceleration, you are going to have to start with the force. I can say that A is equal to force on the electron divided by mass of electron. That's going to give me acceleration of electron. Right. So let me just put this over here. So Fe upon Me. Fe is 3.2 into 10 raised to minus 15 divided by. I hope you remember the mass of electron. I asked you to remember these values. 9.1 into 10 raised to minus 31 kg. Right. So what we've got now is division that I'm going to leave for you. So what we have is, there will be a big power over here, about 10 raised to, when you use scientific notation, you are going to get 10 raised to 15 meter per second square. Some number over here, 0.33 something. Okay, so this is going to be the acceleration of the electron, right, as it falls down. Now we have to find out time in which it will fall from here to here. So because the acceleration is constant, you should immediately use the equation of kinematics. So hopefully you will be able to identify the correct equation to use. I hope you remember there are three. Which one shall we use? We should use the second equation of kinematics because we are interested in finding the time. Okay. So the second equation is delta x is equal to v0 t plus half a t squared. Right. Delta x is the displacement from here to here. I'm taking downwards as positive. You can say so. 0.015, 1.5 centimeter is equal to initial velocity 0. You can say that the electron was dropped. It's falling plus half acceleration. We have already got it over here. I'm just going to write AE t square. So all you have to do is to find out the time. Do this simple calculation. Okay, so I'm leaving that part to you, right? Okay, and just like this, you have to solve. After you've done this, you have to solve the part B of this problem. Okay, so let me just write that over here. This example 1.8, its part B is to be done by yourselves. Okay, because it's the same. Instead of electron, you have a proton. Okay. Finally, the question says we have to compute the time of fall in each case, and it says contrast the situation with that of free fall under gravity. Contrast that is we have to see what's the difference. Okay, right? The difference is that in free fall under gravity, the time does not depend on the particle. I hope you remember that simple demonstration that I did very early in the class. It is that if you take two objects and you allow them to fall, you drop them from the same height, they fall at the same time if we somehow ignore or neglect the air resistance. Okay, but here it's not going to be the case because of the fact that electric forces do not depend on mass. As you can see, this one, have a look here, the force on the electron does not depend on the mass of it. Right? So that is what changes. In gravitational force, gravitational force obviously depends on the mass of objects. That's not the case here, and that's why you're going to see a different kind of behavior. Okay, so obviously electron will fall fast, proton will fall slowly because it has more mass, right? Okay, so that's all about this example 1.8. Now I'd like to ask you to solve something for homework. Right? Let me just have a look. I want you to solve exercise question 1.8. I want you to solve exercise question 1.8 as homework. Okay, let me just write that over here. Entire 1.8 as homework. Okay, and I'd like to give you a hint about this one. The hint is that electric field is a vector. Okay, electric field is a vector. Right? I'm going to solve this problem in the next lecture. Okay. So make sure you solve this before you go on to the next lecture. Alright? So that's it for this one. Goodbye. See you all again.